All right. Welcome everyone to our next meeting of the Dynamics and Number Theory seminar. New England, but now we're moving to the West Coast. And I'm very happy to see Doug Lind from the University of Washington, who will talk about decimation limits of algebraic actions. Over to you.
Great to be here. Thanks very much for the invitation. Let me share my slides here. Can everyone see that okay?
Yeah.
Okay. Okay, so I'm going to talk about decimation limits. This is joint work with Eliza Klaus and Evgeny over a number of years. And this is my first Zoom talk, and so please excuse my amateur attempts at giving a talk. I decided that instead of the usual Beamer slides filled with notation that I can't understand, I'd like to try to communicate the ideas using simple examples and pictures, so that hopefully this makes more sense to you than Beamer slides. So I'd like to begin by talking a little bit about algebraic actions. And we'll start with a very simple example. I'm going to take any polynomial f of x, a Laurent polynomial, in a single variable, and I'll cook up a compact abelian group xf and an automorphism of that group alpha f. So we'll start with a circle group, R mod z, and we'll look at this gigantic infinite dimensional torus, t to the z, and we will define a subgroup xf of t to the z using f. And the description of this is very simple. Over xf, I look at the coordinates, and all I do is use a linear combination depending on the coefficients of f. In this case, it's 1, -1, and -1. And I add up that z linear combination of coordinates, and I should always get 0 no matter where I do that. So in other words, tf is in xf if it obeys this sort of Fibonacci recurrence relation, tn plus 2 minus tn plus 1 minus tn is equal to 0 for all n. So that's the group. And what's the automorphism? It's just the shift to the left. Now, actually, this is just a fancy way to write the two-dimensional toral automorphism 0, 1, 1, 1, because I can take any two coordinates, say t0 and t1, and if I know those coordinates, I can reconstruct the rest of the point in xf, because t2 is the sum of those two, and then t3 is the sum of the preceding two, and so on. So knowing those two coordinates, I can get the rest of the coordinates easily. And if I pluck off those two coordinates to get a point in t2, and I look at what happens if I shift the point and do the same thing, well, that's just this matrix acting on t0 and t1, because t2 is t1 plus t0. And so this is a way to show that this particular example is just a toral automorphism. So we'll be talking a lot about entropy, and for these group things, entropy is really nice. The topological entropy is the same as the Haar-measure theoretic entropy. And there's a familiar formula for toral automorphisms that entropy comes from expansion by the eigenvalues. And so the entropy of a toral automorphism is you just take all of the eigenvalues of A and you add up the logs outside the unit circle of a absolute value out bigger than or equal to 1. In other words, this is just the sum of log plus of mod lambda, where log plus is the positive part of the logarithm. There's a related quantity called the logarithmic Mahler measure of f, and this is defined to be just the integral of log mod f around the unit circle. And we can use a formula that's called Jensen's formula to evaluate this. Jensen's formula, little exercise in complex variables, is that this integral around the unit circle is just log plus of lambda. Now, if we look at the example we have, f of x has roots, the golden ratio, and its algebraic conjugate. And so if we compute the Mahler measure of f, just feed the formula into for f of x into this example, we'll get log plus of lambda, that comes from this part, and log plus of mu, that comes from this part. And you add those together, log plus of mu is 0, and you'll just get log lambda, and that's the entropy of this toral automorphism. So the slogan is entropy here is computed by Mahler measure. Okay. I'd like to give one other example in the single variable case, and this is the polynomial 2x minus 3. So the linear relation is that 2 times this coordinate minus 3 times this coordinate is always equal to 0. Now the Mahler measure of this is log 3. You can just compute that easily using Jensen. But the only root of f in this case is 3/2. And so the entropy, log 3, isn't equal to the log plus of the roots of f. So what's going on? Where's the missing log 2? Well, it comes because actually xf contains 2 eta coordinates and 3 eta coordinates in addition to the normal real coordinates. In fact, you can picture xf as being fibered over the circle. And the kernel of this is an algebraic map, a homomorphism. And the kernel of this looks locally like the 2 adics times the 3 adics. So this is, in a sense, a 3-dimensional object. There's a real dimension, a 2 adic dimension, and a 3 adic dimension. And the automorphism alpha f is just multiplication by this eigenvalue 3/2. But here, the 3/2 come in different flavors. The brown 3/2 corresponds to the reals. The red 3/2 corresponds to the 2 adics. And the green 3/2 corresponds to the 3 adics. And then you have to figure out the expansion in each one of these coordinates in order to compute entropy. Now, 2-adically, 1/2 is big, 3/2 is big. It's outside the quote unit circle. 3-adically, 3/2 is small, and so this log plus is equal to 0. It's a contraction 3-adically, an expansion 2-adically, and an expansion in the real direction as well. So if you add up the logs of these expansion constants, you'll get log 3/2 plus log 2, and you get the correct answer, log 3. So I want to point out that in this business, it pays to have a sort of adelic point of view. You want to look at all completions of the rationals, not just the real completion. And that comes up in many instances, not so much in this talk, but when you're looking at this stuff, the adelic point of view turns out to be quite important, and a notion of p-adic entropy. Okay, what's decimation? Well, decimation is what happens if you start crossing out coordinates. So let's take our standard example, x squared minus x minus 1, and look at a typical point here and cross out the odd coordinates. So we'll cross out t minus 1, t0, t1, and what we have left is the restriction of this point to the even coordinates. So I'd like to describe what this group is. It's certainly a group under coordinate-wise addition, but what's the defining polynomial? How do you get a relation among these coordinates from the original one? Well, let's see if we can figure it out. Let's see if we can get T4 as a combination of T2 and T0. Well, we know that T4 is T3 plus T2. But that's not the complete answer because we've got an odd coordinate there. We've got T3, but we know T3 is T2 plus T1. And we're still not done because T1 we want to get in terms of even coordinates, but T1 is the difference. It's T2 minus T0. And so we'll get minus this plus this. So that allows us to say that T4 is 3T2 minus T0. Or in other words, the defining polynomial for this decimated action is x to the 4th minus 3x squared plus 1. Okay. And that's called the second decimation of F. Algebraically, what we're doing is just taking the principal ideal generated by F, and we're intersecting it with this subring of just even powers. And in commutative algebra, this is just the contraction of this principal ideal to a subring Z bracket plus or minus 2. And you can obtain this polynomial in a different way. And that's just to multiply f of x times f of minus x. If you multiply that out, you'll get exactly f2. And I'm going to write that suggestively as the product of f of omega x, where omega is one of the square roots of 1. Okay, so that's the second decimation. You can do the nth decimation as well. You just restrict to nz and try to find the polynomial that describes what happens when you do that. And typically, this is given by an operation similar to the one we just had. We'll rotate the variable by all the nth roots of unity and take a product. This is not always the case, and I'll describe that in a little bit in more detail in a little bit. So for our standard example, if you do this, what you'll get is the nth decimation is this product of two high-power monomials, two high-power linear things, and you can expand that out explicitly, and you get this result. That's the nth decimation of this polynomial. Now, I want to keep track of the size of the coefficients. I want to think of the coefficients as being given by a function just not on the integers, but on the reals. So I introduced this notation fn hat, and it's just 1 at 2n. That corresponds to this coefficient. It's this at n. I should use a laser pointer, and it's -1 at 0, and it's going to be 0 elsewhere. So this just keeps track of what the coefficients look like. Now, what's happening is that the support of this is spreading out linearly. Here it's 0 to 2n, and vertically it is increasing exponentially fast. And so my co-author Evgeny, coming from physics, says, well, whenever you have a situation like that, you should renormalize and get a limit. And that's exactly what we're doing. We're renormalizing. So the horizontal renormalization is just shrinking things back to the original 0 to 2 interval on which the original polynomial was defined. And we can do that by putting an n in this function. And vertically, things are expanding exponentially fast. And so we take an exponential limit. We take 1 over n log of the coefficient. So when you do that, you'll get, in the nth case, you'll get 0 at 0. You'll get 0 at 2. These are log 1. And at 1, you'll get something which is about log lambda. It's the 1 over n log of this combination of nth powers, and mu is less than 1. And so it converges lambda to the n minus u to the n is essentially lambda to the n. And as n goes to infinity, if you take the convex whole of this, and you take a limit as n goes to infinity, you'll get a polyhedral function, which looks exactly like this. And the convention here also is that off of the support, where this function is 0, log of it is minus infinity. And so off of the support from 0 to 2, this function is minus infinity. So that's the decimation limit of this polynomial. I want to introduce two other things in order to describe this decimation function. The first is the Ronkin function of f. So the Ronkin function is just simply this integral of log mod f. It's like the Mahler measure, except you have a scaling factor of e to the r in there. And so in particular, the value of the Ronkin function at 0 is just the Mahler measure of f. So let's compute the Ronkin function of our example. F is this product. And we can feed that into this formula, and we'll get this integral plus this integral. Now, this e to the r can be factored out of each term, and that will contribute an r when you take the logarithm, and so you'll get a 2r. And then what's left is, by Jensen, you put the e to the minus r on lambda and e to the minus r on mu, and by Jensen, you'll just get this log plus of e to the minus r lambda and e to the minus r mu. So what does that look like? Well, when R is big, these are small, the log pluses are 0. And so when R is big, you'll get a line of slope 2R. When R is large negative, these are huge. Both this and this are huge. The log pluses are just logs. So you're getting 2R minus R minus R plus log lambda plus log mu. But lambda times mu is 1 in absolute value, so you'll just get 0. In other words, for a large negative, here you'll just get 0. And in between, one of these takes over, but the other doesn't, and you'll get a line of slope 1. And that's the Ronkin function of this particular polynomial. The other idea is something called the Legendre transform of a convex function. And roughly speaking, this is just a way to describe a convex function by its support lines. It's an alternative description by using an envelope of support lines. So specifically, how do you define it? You take a convex function phi of r, and I'm going to define the Legendre transform at a particular value u. So I take a line of slope u, I raise it up until it just touches the graph, I trace it back to the vertical axis, and where it intersects the vertical axis, I'll get the negative of the Legendre transform of phi. That's minus phi star of u. The minus sign looks a little funny. Turns out you need it if you're going to do duality. In other words, the Legendre transform has this beautiful property that phi star star is equal to phi. And it really is a dual operation. Okay, well, let's try to compute the Legendre transform of our Ronkin function here. Or rather, more accurately, the negative of the Legendre transform given by this sort of geometric operation. By the way, if there are no support lines for a particular slope, if there is no way to have a line of slope u totally beneath the graph, then the negative of the Legendre transform is defined to be minus infinity. Okay, so what is the Legendre transform of 0? Well, we take a line of slope 0, we raise it up until we hit the graph, we'll hit it here, and this intersects at 0. So the Legendre transform is 0 at 0. If I have a negative slope, I'll never be able to get below this graph, and so it's minus infinity on the negative real axis. Similarly, past 2, a slope which is too steep, again, never gets below the line, and it's minus infinity past 2. Now, in between, if I take a small positive slope and I raise it up, this will intersect at a small positive quantity. And in fact, it increases linearly up to log lambda. If I go beyond slope 1, then the pivot point changes from here to here, and I'll get a line that looks like this, which hits the y-axis there. It pivots around that second corner, and the Legendre transform decreases down to 0 again. So we've described the Legendre transform of the Ronkin function, or rather its negative, and this is exactly the decimation limit of f as we computed before. And that's a general fact that is true in one and actually several variables. One other comment I'd like to make is that decimation limits live in the tropics. So what do I mean by that? Well, there's this object called the tropical reals, which are just the reals union minus infinity. And there are these tropical operations on the tropical reals. It's called the max plus algebra. The tropical addition is given by max. The tropical multiplication is given by a usual addition of the reals. And this turns it into a semi-ring with all the usual algebraic operations. The one big difference is you can't subtract in the tropics. There's no way to subtract things, you can only add them. So what would happen if I tried to do a tropical convolution of two functions in this tropical arithmetic? Well, the usual convolution on R is given by the formula you all know, that's this. But the tropical convolution is given by the tropical analog. The integral in the usual convolution is just a continuous sum, so you would replace max in the tropical edition by sup over a continuous number of reals. And so you would start replacing the integral by the sup over s. And then this multiplication corresponds in tropical things to addition. And so it's the sup of phi of s plus psi of r minus s. And that's the tropical convolution, phi star circle of psi at s, at r rather. So let's compute this on some simple examples just to get an idea of what's going on. So the decimation limit of x minus lambda has the constant term goes like lambda to the n, so you'll get a log lambda, and it looks like this polyhedral function. The same thing with mu. This is a minus lambda down here. And let's try to compute the tropical convolution. So for this, you need to take this and flip it around because we're looking at minus s, and then translate it by various amounts and add it to the original dx minus lambda. And so the amount r that you're translating will, things will depend on the amount that you're translating. If the r is negative, if you're way over here, and you try to add those up, you'll always get minus infinity. And so you'll have a minus infinity for all negative r's. And similarly, if you go way over here and you try to add that, you'll always get minus infinity as well. And so it's minus infinity here. But as you start to move this, this function starts to subtract off not quite as much as log lambda, and the max will increase linearly to log lambda. And then when you move on past 1, you'll get another thing decreasing. You'll get a decreasing linear amount, and it shrinks back to 0. So that if you take the tropical convolution of these two monomials and you look at it, you'll get the decimation limit, which is the decimation limit of the product. And this is true in general. The decimation limit of the product of two functions is the tropical convolution of the individual decimation limits. So it's a kind of tropical object. Now, there are some subtleties here that I've been skipping over so far. The first is that I said there's a single polynomial that describes the decimated thing. In other words, when you contract this ideal, you'll always get a principal ideal. That's not so obvious, especially if you're looking at several variables, as we'll get to. But it's true. The proof uses the heights of prime ideals. These are prime ideals of height 1 and a principal ideal. The going down lemma for dimensions in commutative algebra, and it extends to the d variable case as well. So we always do get a principal ideal, but it's not always the one generated by Fn. Fn can be overkill, and let me give a couple of simple examples of that. If you started out with x squared minus 2, and you contracted down to the subring zx plus or minus 2, you'll just get back the principal ideal generated by x squared minus 2, because x squared minus 2 is already in that ring. But if you computed f2, you would have to take f of x times f of minus x, and you'd get the square of the generator. So that's a simple example where f2 is actually a power of the generator. It isn't the generator itself. And this can happen in more interesting ways. I've given one example here where I've taken the golden ratio and its conjugate and multiplied by various powers of the fifth root of unity. You'll get an irreducible polynomial in z bracket x. It looks like this. And its fifth decimation will be a square, because this factor, if you take the fifth powers of those roots and the fifth powers of those roots, the omega powers all go to 1, and you'll get a square factor here, another square factor here. And again, it turns out that F5 is a square of the generator. And in general, what happens is if F is irreducible, Fn is a pure power of Gn, and the Ens you can compute more or less explicitly. They're periodic, and you can compute a decimation limit both from the Gns as well as the Fns. There are also some diophantine issues that taking the convex hull covers up as well. So let's take this example, fourth degree polynomial. The configuration of the roots looks like this. We've got one outside, one inside, and two on the unit circle. This is a Salem number. And everything works fine, except when you start to look at the 2th coefficient of the nth decimation. Because there, the 2th coefficient is products of pairs of nth powers of roots. Well, the biggest one, the one that controls everything, is lambda to the n times either this root, the nth power of that root, or the nth power of that root. And that means you'll get lambda to the n times the absolute value of these two nth powers. And so 1 over n times this is log lambda plus this other term. And that other term, it never gets bigger than 0. So you'll never see it when you take the convex hull, because you're always below the convex hull. But in principle, cosine can get very, very, very close to 0. And so the log of the cosine could get very, very, very negative. And this coefficient, even with averaging 1 over n, could bounce up and down and up and down and up and down and never actually settle down and converge. But in fact, it does. And that's a diophantine result of Gelfand applied to this case, that these algebraic numbers, which are on the unit circle, the powers never get very, very close to 0, never get exponentially close to 0. And so by this old diophantine result, in fact, the coefficients here can always converge as well to the convex hull. And when I was preparing this talk, I kind of wondered to myself, I think this is true in general, and it must be some almost trivial consequence of some powerful diophantine thing. The issue comes up when you've got a bunch of roots all at the same absolute value. And so diophantine experts out there can probably, if you get bored with the talk, come up with a proof of that. So let's just summarize what we have for z actions. So we started with a polynomial f. We got a decimation limit, which was the uniform limit of the convex hull of these renormalized things on the Newton interval, on the interval on which these things are defined, and minus infinity off that interval. The maximum of this decimation limit is the entropy of the algebraic action. We can compute this by using the negative of the Legendre transform of f, the Ronkin function of f. And these obey a sort of tropical relation that the decimation limit of f and g is the tropical convolution of f with g. Okay, well, let's move on to z-squared algebraic actions. And the generalization should be pretty straightforward to you by now. We start with a polynomial now in 2 variables instead of 1, f of xy. And I will again create a group xf, and now a z-squared action alpha f. And we'll do it by an example, 1 plus x plus y. I like to kid with Klaus that we spent the last 25 years of our lives trying to understand 1 plus x plus y. And we're getting there, we're starting to understand it, but there are still many mysteries that this polynomial holds. So what is this xf when at f is 1 plus x plus y? Well, you look at all elements in t to the z squared, for which when you add up this and this and this in this L-shaped configuration, you always get 0, no matter where you look. And that defines the group. The automorphisms are just the left shift and that's the left horizontal shift and the vertical shift down. And those are the two automorphisms that you get. Okay, so for example, this is z squared is an amenable group. You can define entropy for it. And you ask, what is the entropy of this particular z squared action, this algebraic action? Well, again, it turns out to be the Mahler measure of the polynomial, the two-variable version. The entropy of alpha f is its double integral. It's about 0.3230 if you compute it. But, you know, this looks mysterious. How could you possibly guess a formula like this? What does Mahler measure have to do with entropy? So let me give you some motivation for this. So you can think of the horizontal shift on t to the z or complex coefficients or whatever as having eigenvectors. If you take a theta between 0 and 1, and you look at the doubly infinite sequence, which are just the powers of e to the 2 pi I theta, that's a sort of infinite dimensional vector. And if you shifted one to the left, you'll just multiply that vector by e to the 2 pi I theta. So that you have this sort of continuous set of eigenvectors with a continuous set of eigenvalues, one for each element on the unit circle. Now, what's the vertical shift look like? Well, you've got a sort of toral automorphism, except on the infinite torus. And this condition that we have really says that when you shift this down, this coordinate is minus this coordinate minus its shifted coordinate. In other words, the vertical shift acts just like the identity minus s. And we know what the eigenvalues of that are. They're just -1 minus these elements on the unit circle. So if there's any justice in the world, if you believe in continuous sort of limits of finite approximations, for a toral automorphism, you add up log plus over the eigenvalues. So here you should integrate log plus of these eigenvalues. In other words, this entropy should be the integral of log plus of those eigenvalues. Now, each one of those log pluses you can apply Jensen to. And when you do that, you'll have another integral with another variable, and you just throw that in, and Jensen tells you that this integral is equal to this integral. And that integral is just the Mahler measure of 1 plus x plus y. So that's a quick explanation for why the entropy should be the Mahler measure in this case. But to actually make rigorous sense of that is actually quite complicated, partly because f vanishes on the unit torus, so you've got logarithmic singularities to worry about, and so on. So I won't go into further detail, other than to say when Klaus and Tom and I were trying to prove this initially, and this was the key example we had to understand, I've never made so many mistakes in a proof in my life. It was just horrible. I just kept making mistakes, but we finally got it right. So I'd like, before going on to decimations in z squared, to make a little non-commutative interlude here, because this has really been pretty interesting developments. So this is to the side, but still, I think, pretty interesting. So let's look again at our polynomial f, which is 1 plus x plus y. And you can think of it as an element in little L2 of z squared. It's just got 3 non-zero coordinates. And so you can use that to convolve by f hat, and you get an operator convolution by f hat on little L2 of z squared. Now, operators in this setting have something called the Foulet-Keteson determinant. This is a generalization of essentially the absolute value of the determinant of a finite dimensional matrix. And it's essentially an exercise to prove in this case that the log of this determinant is the Mahler measure, and that's the entropy. Well, in 2005, Christopher Denninger at Münster realized that this could be a way to compute entropy for algebraic actions, but with non-commutative groups where you don't have Mahler measure, because this convolution operator is always defined. And entropy is certainly defined, at least insofar as amenable groups. And there's a kind of a funny story behind this. He was sitting around the lounge at Münster one day, and his fellow faculty member, Wolfgang Luke, comes up to him and he presents him with this huge, thick Springer book that he's just published on L2 invariance and torsion and Betty numbers. And he doesn't know what to do with it. I mean, he doesn't know anything about this stuff. So he starts sort of absent-mindedly flipping through just to see if he recognizes anything. And he stumbles on this example that Fugleiter-Kedersen determined it is Mahler measure in the abelian case, in the ZD case. And it then occurred to him that you can actually use this to replace Mahler measure and compute entropy. And that's exactly what he did. He showed that for certain amenable groups, this does work. And that was extended through a number of other people to the general case by Haofeng Li that this is true in general. Well, in 2008, Bowen extended the notion of entropy to actions of sulfate groups, discrete sulfate groups, including the free group on any number of generators, which was a total surprise. There was an example that had mentally blocked everyone from thinking you could do this for a long time. But he broke through that block, and now there's a well-developed notion of sulfic entropy. And in 2016, Ben Hayes showed that this formula, you can sort of eliminate the middleman here, and entropy is now defined because it's a sulfic group. Log det is defined just in general, and Ben Hayes proved the ultimate general theorem that entropy is computed by the Fugleiter-Kedersen determinant. So you might think that's the end of the story. That's great. But, I'm a computational guy. I like to know things to within, 2 decimal places. So suppose you've got X and Y are the generators of the free group, and you want to know what the entropy of 1 plus X plus Y is. Well, I'll tell you the answer. The answer is a half log 4/3, but there's no rigorous proof of this. The meaning of this is simple to describe. So take 2 very, very, very large random permutation matrices, P and Q, and you look at I plus P plus Q. Now, there's no reason to expect anything nice about the eigenvalues because P and Q don't commute, and it's difficult to see what you could say about this sensibly. But the beauty of free probability theory and random matrix theory is that, in fact, you can say a lot about these eigenvalues. Here's an example I did in Mathematica, 3,000 by 3,000 permutation matrices. That's what the eigenvalues look like. And the sort of computational content of this is that if you average the logarithm of those eigenvalues, you should get something very close to a half log of 4/3. In fact, there is a conjectural limiting distribution for these eigenvalues, and it looks like this. And you get a half log of 4/3 by simply plugging this into Mathematica and computing the interval of log mod x against that. When I first did this, an outcome came a half log of 4/3. I think it's the only time I've used Mathematica and then burst out laughing. You get a very simple answer. I expected a decimal, and that was it. I think the whole subject of algebraic actions over the free group is incredibly interesting. Klaus and I just showed that 3 minus x minus y, let's see if I can do this, 3 minus x minus y. If you look at that, the algebraic action is measurably conjugate to the Bernoulli 3 shift. And that's the first example of a free group action which is provably Bernoulli, for which there is no obvious independent generator. So, but there's lots and lots and lots of really interesting questions that haven't been answered. Okay, z-squared decimations. So again, you just restrict to coordinates now in the lattice nz squared, the two-variable version of Fn is just rotating by the nth roots of unity here and the nth roots of unity here. So if you take, for example, 1 plus x plus y and do this when n is 5, you expand it all out, you get this complicated looking polynomial. To renormalize, you will rescale by n squared in each direction, and then average the log, take 1 over n squared times the log of the coefficients. And what happens here is that by rescaling by n squared, the places where this is non-zero start to become more and more densely sprinkled around the unit simplex. So that when you do this, for example, when n is 5, you'll get this. You'll get a polyhedral surface over the unit simplex. If you do this with more points, the points become more and more densely distributed. And here's the illustration for 30 points, the 30th decimation, starting to look like a very nice smooth surface. Now, there's an interesting coincidence because Okunkov published this really cool survey article on random surfaces in the Bulletin in 2015. And in his article is the graph of a function, which is the same function. It comes from a completely different set of mathematics. It was originally discovered by looking at random lozenge of tilings that look like this, and a dimer model in statistical physics. And this function is called the surface tension for the model, and it has exactly the same formula. But it's not clear the connection. Evgeny may be able to fill us in a little bit more from his physics background on this. But what's really curious is that this decimation limit does come in a completely and totally different way using statistical mechanics reasoning. Well, I'm just going to now briefly go over the sort of two-variable version because it's a pretty straightforward generalization of the one-variable version. The Ronkin function now is a function of two variables. You rescale by these two things. And you can compute this as, again, a convex function. And it's a convex function which is flat on the complement of the amoeba of F. And this is just the image under the log map of the variety of F. You can also define the Legendre dual of this Ronkin function now by using support planes rather than support lines. And what you'll get is, let's see, I guess, and what you'll get is that the negative of the Ronkin function, the dual, is the decimation limit. So again, I like to compute things, and so I'd like to see what this is in 1 plus x plus y. Can you actually compute this as a function of the coordinates in the unit simplex? And you can. This is a very sort of deep, it's a kind of an involved calculation. But in the end, what results is if you take this auxiliary function b of rs and you can use this auxiliary function in this part of the simplex. This is less than or equal to 1. In this part of the simplex, it's greater than or equal to 1. This is a symmetric function, and so we only need to compute it in the lower half of the simplex. And in the reg triangle, there's a nice power series formula for it. It looks like this, and using nth powers, where b of rs is less than or equal to 1, this converges absolutely. In the other part, in the green part, you'll use negative powers of b, which is again convergent, absolutely. And the max of this function is at the median point, 1/3, 1/3. And if you plug this value for RNS into this formula, either one, you will end up getting the Mahler measure, and that Mahler measure was computed by Chris Smith a long time ago by this explicit formula. So that's just an example of how you can explicitly compute the decimation limit in this example. So the ZD versions follow exactly the same pattern as for one variable. The renormalized things converge uniformly to the decimation limit on the Newton polyhedron. You can compute it by the negative of the Legendre dual of the Ronkin function. The max is the entropy, and there's this tropical convolution operation that corresponds to polynomial multiplication. So let me just make a couple of quick remarks about the proof. Key to this is the Mahler estimates. The one variable, which was in his original paper, is a very simple combinatorial argument that the coefficients are bounded by these binomial coefficients times the multiplicative Mahler measure, this e to the additive to the logarithmic Mahler measure that we've been using. And you can induct your way up to several variables. For example, two variables, this is the Mahler estimate. And we use this to show that if coefficients are big, then Mahler measure has to be big. That's basically what's going on here. But it is there's a trick here. There's a trick because the decimations are polynomials in nth powers, not just general polynomials. And so we can shrink those things down to be real polynomials in 1 over n times the exponents. And when you shrink that and apply Mahler's estimates, you save a factor of n, and that's what is really making the proofs work. And as we found out later, actually, Boyd used exactly this kind of argument to show that the Mahler measure is a continuous function of the coefficients. That's not so easy to prove, by the way. I challenge you to try to do that. What happens, the subtle point is what happens is if a coefficient goes to 0 at like the boundary of the Newton polygon. For example, in this case, if you compute the Mahler measure, you'll get log of epsilon from this coefficient, and then plus the log of the first log plus of the first coefficient, first root plus log plus of the second root. This first root, so log epsilon goes to minus infinity. This first root is going to infinity, and the second root is going to 1. And you just have to show everything balances out and gets you 0 in the limit. So even in this simple case, it's not so obvious. Mahler measure is a continuous function of the coefficients. So let me just end with a couple of questions. The first question is, are there finer convergence results for all the coefficients? So we saw even in the one variable case that one coefficient was bouncing up and down, but it actually converges to the correct thing by a diophantine result. Does the same thing hold for general polynomials, or can you have some sort of bizarre bouncing up and down behavior for some of the coefficients? Who knows? I just don't know. It's a very complicated question, I think. The second is there a sort of random walk explanation of decimation limits? So what do I mean by that? Well, how do you get in the 1 plus x plus y case? Remember, you're multiplying 1 plus omega x plus zeta y over omega to the n equals 1 and zeta to the n equals 1. So you end up getting 3 to the n terms. So renormalized, how do you get the coefficient in the middle of the simplex that looks like this? Well, you'd have to get, if you do this, you'd have to get Rn of the terms being the x things, Sn of the terms being the y thing, or Rn squared being the x part, Sn squared being the y part, and some complementary stuff for the ones. In other words, to get this coefficient, you just have to compute this sort of over all possible paths going here. It's a kind of random walk, and each path has a weight, and that weight is equal to a product of roots of unity. And you add all of those things up, and somehow, when you do that, it has an exponential growth rate. But that doesn't seem to fit into any of the standard random walk things, because these are not independent processes, these are sort of Kronecker processes. And the funny thing is, for 1 plus x, but we know the answer. We know exactly what has to happen when you add all of these things up. It grows like the decimation limit at that point. But is there any kind of random walk explanation for why that should be the case? Don't know. It's a very tempting sort of random explanation that may actually be a very interesting mathematical problem. Another question is, what happens if you have two polynomial conditions, x and g, f and g, and here entropy is 0. You kill off the entropy, and I think if there is a theorem, you should probably decimate along subspaces rather than in the entire lattice. And finally, a question is whether you can replace ZD with any residually finite group. Certainly the questions make sense, and you might actually get some interesting questions. Okay, I think that's pretty much what I wanted to say about decimations. I've prepared a little diophantine dessert as well with sort of related questions, which I think we still have some time for, but maybe it's a good time to stop for the moment and see if there are any questions from anyone.
Okay, so let's stop for a moment and give Doug a round of applause first, either virtual or in real sound. Yeah, if there are any questions, please go ahead. I think we have time to maybe take a short break if we want, or just go on and have dessert after the main course. So, any questions, please go ahead. Yeah, if not, I don't know. I'm ready for dessert. I don't know how.
Okay. So here's the dessert. To compute Mahler measure, you're just integrating log mod f over the unit circle or over the unit torus. Okay? And the question that I'll ask is, if you try to approximate this integral by a Riemann sum, do the Riemann sums converge to the integral or not? Now, if f doesn't vanish on the unit circle, log mod f is a continuous function, and this is trivial. But if it does vanish on the unit circle, it's not so trivial. So here's our example that we had before, where there were two roots on the unit circle. Log mod f looks like this curve, and it's got two logarithmic singularities. These are integrable. This is an L1 function. These are integrable singularities. But the question is, if you took equally spaced points along the nth roots of unity and computed the Riemann sum for them, does that converge to the Mahler measure? See, what can happen is one of these roots of unity could be incredibly close to the singularity, and then log of that could be incredibly negative. And if it's incredibly negative, it could throw off the Riemann sum approximation. In fact, in principle, it could go to, some of them could be close to minus infinity. Well, if f is a polynomial with integer coefficients, these points where the singularity happens are, again, algebraic numbers, actually here algebraic integers. And Gelfand's result says that the nth roots of unity never get exponentially close to the singularity. And so in this case, the Riemann sums converge to the integral for sure. But that's essentially equivalent to Gelfand's theorem. And that's a hard theorem. Okay, so that's the question. Why are you interested in Riemann sums? Well, dynamically, if you try to compute the number of periodic points for one of these algebraic actions, you get Riemann sums. In the case of a single Z action, the e to the Riemann sum is the number of periodic points. points. And so if you want to compute the growth rate of periodic points, you're looking at Riemann sums. And in this business, the growth rate of periodic points, as far as we know, always converges to the entropy as a limit. We don't know of any counterexamples to that. So that's the motivation for looking at Riemann sums. What's crucial here is what we're calling the unitary variety of a polynomial in D variables. This is just the places on the multiplicative torus where the function vanishes. And for several variables, you can have all sorts of Riemann sums. In fact, you can look at Riemann sums over finite subgroups of the torus, which may not look quite as uniform as the nth roots of unity in each coordinate direction, but could look, for example, like the 10th roots of unity here and the billionth roots of unity here. They can be very, as long as they get denser and denser, that's an allowed collection of Riemann sums. And then the question is, do the Riemann sums in this more general sense converge to the Mahler measure? So here's some examples to look at. Our example 1 plus x plus y. The unitary variety of F is just these 2 points. Those are cube roots of unity. And its dimension is 0. Another interesting unitary variety is in 3 variables, 2 plus x plus y plus z. You get this sort of twisted curve. This is actually a one-dimensional curve. I had to thicken it up in Mathematica to make it look, so you could actually see it. So this is a one-dimensional thing in a 3-dimensional torus, so it's got codimension 2. And those are 2 good examples of thin unitary variety. And by thin, I mean not codimension 1. So if the dimension of the unitary variety is less than or equal to the number of variables minus 2, that's thin. So this is thin, this is thin. So here's the theorem. The theorem is that if the unitary variety is thin, then the Riemann sums over all finite subgroups converge to the Mahler measure of F. Okay. And what's really interesting is that there are three completely different proofs of this theorem. The first was Klaus and Evgeny back in 2013. We used a completely dynamical argument using homoclinic points. You want to drive up the number of periodic points. You want to show you've always got enough periodic points. And homoclinic points are a technical mechanism for creating oodles and oodles of periodic points. And so we were able to show this convergence using this dynamical operation of homoclinic points. Then Vesel and Dimitrov came along, and as part of his thesis, I think at Yale in 2016, he gave a completely diophantine explanation and argument for exactly this same phenomenon. And he did a lot more, of course, but in particular, he reproved this result using completely diophantine arguments. And then he and Heberger, Vesselman knows everything. I mean, he's amazing. It's just incredible. But he observed that some stuff Heberger had done on rational points near definable sets could also be used to prove this. And they have very recently published a paper in which they reprove this and get quantitative estimates on how fast the Riemann sums actually converge. And again, they do a lot more. They're looking at Galois orbits of roots of unity, and it's a much subtler sort of thing. It's a much stronger result. But in particular, they recover a quantitative strengthening of our original thing. What is interesting is every single one of these proofs break down in the codimension 1 case for very different reasons. In our case, it just doesn't get off the ground. You can't get homoclinic points in the codimension 1 case, none. And so, or at least none that are useful. So we can't even get started with the dynamical argument. And there were apparently, and I don't pretend to understand these papers completely, other very difficult, lots of difficulties in trying to extend this to the codimension 1 case. So here's an example. if you look at this polynomial, its unitary variety is just a curve. So this is codimension dimension one in a two-dimensional torus. That's what log mod f looks like. And the question, which is still open, and in fact explicitly described in the Dimitrov-Heberger paper from last year, is do the Riemann sums over finite subgroups of this converge to the integral? Let me point out there's a slight issue here, namely that if the curve has roots of unity on it, then you have a value of the function which is minus infinity, log 0. In this particular case, there are 4 roots of unity. Those turn out to be related to sixth roots of unity. Actually, there are no other roots of unity on this curve. That's a nice exercise. But when that happens, you just throw those away. Dynamically, there's good reason for doing that, and you just ignore the places where it's minus infinity. Here's just a finite number of points. So wide open is whether the general convergence results suggested by dynamics are true. Dimitrov can show that if you use square subgroups, in other words, nth roots of unity in each coordinate direction, it does converge. So he has enough diophantine stuff in order to prove that. But the general general question about Riemann sums, even in this example, is still wide open. So that's the end of dessert. Thanks.
Okay, all right. So I guess it deserves another round of applause. Any questions for the dessert or for other parts of the meal? I guess I need to quote a message sent by Tushar Das in chat that I shudder to imagine how good your second Zoom talk would be. It was really beautiful talk. I completely agree.
Thank you.
Other questions, comments?
Hi, Doug. It's Emmanuel. Let me. So I don't know why, but oh, there I am. Hi, Doug. Can you say one word about your motivation to study decimation? Is it? I mean, what's the initial? What was your historically? What's the?
This is Evgeny. Evgeny comes from physics, and they renormalize all the time. So Evgeny, I mean, you're the guy who came up with this idea. So could you explain?
Okay. First of all, I don't come from physics, but idea comes from physics.
Okay.
So if you have anything that's idea coming back to Wilson and people Fisher and statistical mechanics. So if you look at the Ising model on ZD lattice, then you decimate, and then your interaction, your Ising model should remain Ising model plus some corrections. So you're going to the fixed point of renormalization procedure. And so it's kind of a fixed point, and then the eigenvalues along the, I don't know, stable or unstable directions are the critical exponents for them. So the interest in decimations and the coarse graining of the system is computation of critical exponents in Ising models and of N-dimer models, which are also critical.
Okay, that makes sense. Thanks a lot.
Let me point out that those guys, you know, it's Kunkov, Kenyon, Sheffield have done a tremendous amount of work on this stuff. But they get there's a collection of polynomials which are closely related to these physical models, and they get similar sorts of things, you know, Ronkin functions and Legendre transforms and stuff. But those are very special polynomials, and so I just want to emphasize that what we've done here is for a completely general polynomials, any old polynomials of the variables. But they also get stronger. I think they get stronger results. It's very difficult to read this stuff. I mean, I try to read Sheffield's thesis, and it's really obscure.
They get strictly stronger results because there's their coefficients for us it's coefficients of polynomials, and for them it's these are partition functions, so they have physical meaning.
Okay.
And you can do more with the physical meaning.
Okay. And so I had another question on your dessert dog. So this the question is for so the polynomial has integer coefficients. Is that right?
Correct.
Yeah. Sure.
Yeah. Yeah. Or algebraic. Algebraic. It's the same with algebraic number code.
It's the same. Yeah. Okay. Yeah. Thanks.
I mean, the real question is, you take a point which has coordinates which are roots of unity, and you look at the Galois orbit and you see how uniformly distributed that becomes. And can you use a test function which is log mod f, where it has singular logarithmic singularities?
Right. I mean, it reminds me of Bilou's theorem. You know, maybe Bilou's theorem says that when that you get equidistribution of Galois orbits near the unit circle. Yeah. So maybe it's not restricted to finite subgroups, but maybe if you take an arbitrary Galois orbit, maybe it has a chance to converge. As long as the height tends to 0. I don't know.
I mean, what strikes me, there's something deep going on, because you've got 3 very different proofs and they all break down at exactly the same place. So there's something going on that I certainly don't pretend to understand. Yeah.
Okay, so if there are no objections, maybe we can have the last round of applause and stop the official part. Thank you for coming. And it was great to have you.